Hello and welcome back. Hopefully this is not your first research methods video because this is the final one pretty much. This is the final two chapters. I'm compressing it into one video. We're talking about chapter 12 and chapter 13, which is about descriptive statistics and inferential statistics. So as the Westfield's sequence goes, you're taking this class after Psych 101, then sometime in the future, probably next semester, you'll take Psych 308, which is statistics for psychologists, and then the semester after that you'll take research methods 2. The thing about research methods 2 is that it is kind of like this class in as much that it's about research methods, but at least for me, in that class I don't lecture at all. It's literally just hands-on, like doing research for yourself and writing about it, and learning how to communicate scientific findings and being professional about it and all this other stuff. This final chapter is like a way to kind of lead you into that next piece. So have you learned everything that you should know for research methods? Maybe, but honestly, this is, this is kind of the beginning for some of you. Now you have some of the basics. We're going to kind of get a little more complicated, which involves bringing in statistics. Before we move on, though, the point that I wanted to make about that is that this semester, as we've been reading these research articles, I noticed a lot of folks mention oh yeah, the results section looked like a bunch of numbers and jargon, so I just skipped it, which is totally fine. But this chapter is dedicated to that section. It's dedicated to those numbers and to that jargon. And you're going to be spending next semester kind of learning more about what that stuff means and why it's important and how you can do it yourself, and how you can interpret it and critique it and things like that. Alright, so last video I warned that video was going to be about an hour long, and it ended up being much less than that, I think. This one, not going to be the case. This one is definitely going to be about an hour long because we've got 2 chapters to cover. So let's get into it. Here's what we're talking about. We're talking about how we can communicate our data, how we can show it visually, and how we can understand it. So I am not going to be asking you to do any math at all on the final or for this chapter's quiz or anything like that. But you will need to know what numbers mean and why they, like which numbers to use and which figures and graphs to use and things like that. So that's where we're going for this. Alright, so this is a normal distribution. This is kind of the fundamental premise of research, or at least of generalizing to other fields or to other populations, to other sample sizes. So what is a normal distribution? Sorry, I'm getting a little ahead of myself. I'm getting too excited because I usually teach stats. I teach stats more than I teach research methods 1, so I'm trying to put on my stats hat now. So normal distributions we see all the time everywhere around us. If we want to talk about height, let's talk about height, for example. If we're talking about the height of a population, let's take a look at this, where let's say that the height, I want to say, is about 5'8" or something like that, whenever you're including everybody, that's about average. Now if we were to move along that scale, we're going to find some people that are like 7 foot, right? So 7 foot 0 inches, and then on the other end we're going to find some people that are going to be shorter than 4 foot 0 inches. But in both cases those are going to be kind of rare. Those are kind of unlikely. It just doesn't occur that much in our population. But we do have a lot of people that are hanging around this middle part, around 5'8". Maybe we have some people that are a little bit shorter. Maybe they're 5 foot even or something like that, or maybe they're as tall as 6'2" or something like that. But the premise is, and I know these aren't equal intervals, but I'm just trying to articulate the point here. We could change this to 5'2". If you want to make equal intervals, are you happy? So basically what we're saying is that the majority of the population, roughly about 68% in this case, is going to be between 5'2" and 6'2". That's the majority of the population. That is equally likely to find someone shorter than 5'2" as it is to find someone taller than 6'2". That's the idea of a normal distribution. We see, but like I said, we see this all the time. We see this, for example, when we talk about intelligence testing and intelligence scores. That the middleest intelligence score is 100, and then from that we have 85, and then we have 70. On the other hand, we have 115, and then we have 130. And what this means is that what is the likelihood of finding an individual who has an IQ over 130? It's going to be about 2%. So about 2% of the population has a higher IQ score than that. But for the most part, 68% of the world is going to fall between 85 and 115. So this idea of a normal distribution helps us generalize. If we are learning something about a sample's average and try to generalize that to the population, we would expect that it's probably going to be somewhere in this big gap, right? Or this big part. I said gap. I shouldn't have said that. This big part of the distribution, about 68%. But we could also, for example, if I were to, looking back at heights, for example, if I were to go through and look at NBA heights, what do you think is going to be the average height of the Knicks, for example? Probably going to be higher than 5'8". Probably going to be higher than 6'2". Probably going to be, 6'6" and beyond, right? If I had to guess off the top of my head, it's probably going to be quite tall. And so what we would say is that sample is very unlikely to come randomly, right? Because those individuals are going to have heights that are over in this really extreme end of the distribution. And if my entire sample, that basketball team, if my entire sample is way over here, then that might mean that they are not picked randomly. Which, of course, we now know that is true, right? Because it's that by and large, people that are in the NBA are taller than others, right? And so it's not by random chance that they happen to be at the extreme end of the height distribution. That there's a reason why they are, which might be because being taller gives you a competitive advantage in basketball, as an example. So this idea of a normal distribution is going to be the key. This is the center of talking about inferential statistics, which we're going to get to by the end of this video. I'm just laying down the base work here. Okay, let's finally get started. Sorry, that took 7 minutes to kind of introduce. Let's talk about different kinds of figures and tables now. So this is a frequency table. Right here we're looking at the question, how many pieces of candy did you get this past Halloween? And then we have these different intervals, right? We got 18 through 22, 28 through 32, 38 through 42. So we got some really unlucky kids and some really lucky kids, right? And so this is a table. You see it all the time. Not particularly fancy, right? So if you're trying to communicate your data, is this the way that you would want to do it? I think that if this is the data that you have and you're trying to communicate your findings, you probably want to make it a little bit more interesting. You probably want to make it a little bit more exciting, right? So you might want to use something like this, where you're using a frequency polygon, where you're going to take this data and you're going to say, all right, I'm going to plot this out so that way we can see, how many people had so-and-so, and we're going to see something like that, right? Where we see essentially a normal distribution of the candy dispersal. So the frequency polygon is a way of illustrating what we see here in the frequency table, where we are going to plot the frequency, so how many of these data do we have on the y-axis, and then on the x-axis we can have an ordinal scale. It's important here that this is an ordinal scale. It could also be interval or ratio, frankly, but it can't be nominal. There's specific other figures that we're going to use for nominal scales. So here you can see the same data plotted out like this, where now it looks a little bit fancy. Now we have an idea of what the most common treat number is. It's going to be something between 25 and 35, right? All right, so here is another kind of graph called a histogram. A histogram is going to be very similar to this frequency polygon. The only difference is that it looks like a bar graph, or some people call it a bar graph. But what we have here on the x-axis are going to be these intervals. So the interval between $10 and $20, and from $20 to 29, and then from 29 to 38, and from 38 to 47, and so on. And so this gives you an idea of the distribution of different data that you have. So again, right here on the y-axis, you're going to have the frequency, and then on the x-axis, you're going to have those intervals. So it's almost identical to a frequency polygon, if I'm being honest with you. But at least in psychology and in statistics, you see histograms used much more frequently. But again, they help illustrate this kind of nice normal distribution, right? This kind of almost symmetrical kind of rise and fall of the data. Here we have a bar graph. Now here's where I was saying that there are going to be some kinds of graphs that we are only going to be able to use with nominal scales, and bar graphs are one of those. So why is it used for nominal scales? So we have the y-axis. This says x-axis. That is incorrect. My bad. I'm so sorry, y'all. So here on the y-axis you have the frequency, and on the x-axis you have the category. So here, rabbit, dog, cat, goldfish, hamster, why is this different than a histogram? Because if we're moving from left to right, you'll see that this does not belong on a scale. You can't increase the number of rats you have until that rabbit, increase the number of rabbits you have until it becomes a dog, and then if you move further down the scale, that dog doesn't then become a cat, and that cat doesn't then become a goldfish, and so on and so forth. So this is not an ordinal scale. These things are nominal. In other words, they are word-based, they are category-based. So we can't treat this as a continuum. We can't treat this as a spectrum. And that's what makes it a nominal scale. So here we can see what the most popular pet is, which is a cat, right? But we can't look at this like we can't really call this like a normal distribution or symmetrical data, because there is no scale here on the x-axis. Alright, so it's important to look at the details for that reason. So anytime you are looking at data and you're looking at the figures that someone is presenting to you, it's important for you to kind of take a look at what's going on over here on the axes, because you want to make sure that people are doing their job. People screw this up all the time, where they're talking about bar graphs or histograms and they get that part wrong. So you always want to check the axis. And that can also show us some interesting ways where people are trying to deceive us. Believe it or not, people are, and you do see it sometimes in science and research, where people will try to really brag about their data or show it off, and they'll kind of manipulate the figures a little bit to try to do that. But this isn't used so much in research. It's used much more in the news and in advertising. So you definitely want to, in your normal everyday life, whether or not you are a psych major, whether or not you want to be a counselor or a researcher or whatever, one thing that's always going to be good no matter what is paying attention to the axis, because you can see examples like this where people are trying to deceive you. So for example, this person is in this advertisement right here, the sample advertisement, they're saying, look how much better our brand of truck is compared to these other brands. Look how good we are, right? That they're still functioning after 10 years. That's quite amazing. We're so much higher than these others down here. But if you look at the axis, you can actually see that this is actually from 95% to 100%. So this is zooming in on the largest, or the highest 5%. And if we were to zoom out and look at the full scale now, moving from 100% to 0%, you can see there's actually not that much of a difference at all, right? This is basically just a difference of 1%, which is meaningful, but is not as drastic as what that advertisement shows. So it can be helpful to pay attention to these kinds of things. So now that we've talked a little bit about figures, we're going to talk more about figures at the very end, or at the halfway point. I scheduled an intermission that should be kind of fun, where we're going to look at some bad statistics. But it's not just enough to know if someone's trying to deceive you visually, especially with the rise of social media and algorithms that online, especially through social media, that kind of generate content for us. We see a lot of people trying to use statistics to argue their points, or to say that something is true or false. They like to throw data at you. But as you know, you got to be careful, because people will do this maliciously all the time and try to deceive you. So what I'm hoping is that for the rest of this presentation video, the next 45 minutes, we're going to walk through what these stats are, how they're used, and essentially how you can know if somebody's using it appropriately or not. So let's get into it. The way that people talk about their data is the descriptive stats. But you probably guessed that already, right? Just from the name descriptive, it describes stats. So if we want to kind of communicate whether or not something was effective, we might want to talk about descriptives. What is the, how good is this vaccine? Well, I don't know. This guy says that it works. This guy says that it doesn't really work. So what can you rely on? You have to use data, and you have to try to describe the overall big picture of it. So maybe you say, all right, the vaccine is 95% effective, which means that for 95% of people it's going to be effective, and then for 5% it doesn't, it's not as effective. So maybe that one guy we talked to earlier, maybe he was 1 in 20, right? Maybe he was 1 in 20 that it didn't work. I don't know. But either way, that gives you a much clearer picture of the truth whenever you're talking about that. One second, my wife is yelling for me in the other room, so I gotta pause this. How embarrassing. All right. Okay, are we? Yeah, I'm recording. Okay, cool. Sorry about that. So we were just talking about how can you accurately talk about data, right? And so one way to do that is using descriptive stats, where you're showing the difference. You're showing whether or not something is effective by comparing numbers now, right? We can say like, oh, this was 95% effective, and this one was 90% effective. Therefore, we know that 95% might be a better option, right? So whenever I'm talking about that, I'm using that phrase 95%. What does that mean? Basically, I'm saying like, on average, this works for 95% of individuals. That is a measure of central tendency. Central tendency is just a way of saying like, on average, or middleist, or representative. That what you're saying here is that this is roughly what the middle of your data looks like, or it's the most representative piece of your data. But we might also want to talk about the variation. So we might want to talk about, sometimes you hear it called variation, sometimes you might hear it called dispersion, like that. And dispersion is essentially saying how different is your data. So if we think about going back to the height example for a moment, if we were talking about height, that the height in the U.S., 5'8" or whatever. But if we're looking at the dispersion, how different are those? We know that it's quite different, right? We know that people can be up to, like 7'11" or whatever. We also know that some people can be as short as like 3'2". So we know that people vary so much in their heights, which means that there's a lot of variability in the heights that we have. So we would say there's a lot of dispersion there. And so that phrase, a lot, how can we talk about that in a meaningful way? We can find a number that represents that. And that's what the dispersion element of this is. And so descriptive stats, a lot of it is going to be dedicated to these two ideas. The central tendency and the variation/dispersion of that. All right, so and then even then, we can use that measurement of dispersion to know roughly how, and this is looking ahead a little bit maybe, but we can know how uncommon someone's values are. So if we know, for example, roughly the dispersion of height in the United States, if I said, yo, my friend is 5'0", right? Can you believe that? He's 8 inches shorter than the average or whatever. And you look at it and you're like, oh, that's actually not that uncommon, right? Like, I don't even know why you're bringing this up, dude. Like, it's not that, it's not that uncommon. We could know essentially how uncommon a value is by looking at its dispersion and comparing it to the central tendency. If you said, yo, I have a friend who is 9'6", then I would know, like, wait a second, 9'6", are you sure about that? Because we know the range of values that exist in height. All right, so let's talk about some of those measurements now. Let's talk about the first, which is probably the most common, which is the mean. The mean is what most people call the average. Honestly, it's really frustrating that they go by two different things. And once you take stats, we only ever call it the mean. And the reason why is because algebra is usually what people will refer to when they're, algebra. Average is usually what people refer to when they mean common or normal, quote unquote, right? And so that isn't exactly what we always mean when we talk about stats, or we're talking about depicting our data. So that's why statisticians and mathematicians use the phrase mean instead of just average. But that's what it is. It's just the average. And if you know how to calculate the average in algebra, then you already know how to calculate the mean. You're just going to add up all those values, and you're going to divide by the total number of values. And that's going to give you an idea of what the most central or what the most middle data point is going to be. So, for example, if you had these numbers right here, if I said this is how many meals I have, or how many cups of coffee I have a day, 3, 4, 5, 6, and 7. That's one way to answer it. But if you asked and said, like, you know, how much coffee do you drink? I could easily just say, on average, 5, right? And the way that I could do that, and it be descriptive and reflective of reality, is by just adding up those different days and then dividing by the total number of days. The problem with this, though, is that it can be affected by extreme values. And those values, I mean, like really extreme high values and really extreme low values. So if, for example, my average here, if I had 3, 4, 5, 6, and 7, but on Friday I had 17, then you know that this number right here is going to go up a lot, right? And that might be a slightly inaccurate picture of how much coffee I normally have during the day. So it can be affected by extreme values. It also can't describe categorical data. So if your data is something like, you know, what is the average NFL team? What does that even mean? I don't even know how to answer that. Just even trying to think about how to answer that question is weird. It doesn't make sense because you're talking about categorical data at that point. So another example of this would be like the mean IQ of the United States is 100. That was one of the examples that I gave you when I was talking about normal distributions. We can also talk about mean income and things like that. So let's talk about a central tendency value that does not change depending on extreme values. We're talking now about the median. The median is the middle of your data. It's the square middle of your data. You might also hear people talk about this as a 50th percentile. The 50th percentile basically just means that you can divide your data perfectly in half. That if this is the 50th percentile, everything below it is going to be considered below the mean, and everything above it is going to be considered above the mean. I don't know. For the most part, that's not always going to be true, but for the most part, that's what the 50th percentile means, that you have half of all your data lies above this point, and half of all your data lies below that point. So the way to do this is to line up all of your values in order. So here, 5, 8, 3, 5, 2, you know how to, like, all right, so we got to do 2, 3, 5, 5, 8, 10, 53. So the median here is going to be 5. That if I were to arrange this, so again, we got this, right? And I were to cross these out, that's always how I would do it by hand, is I would cross out, you know, moving from smallest to largest and going back and forth until you land on the middle one. So we would say that the median is 5. Why is it useful? Because if I did the mean, if I added these up and then divided by the total number of values, I would get 12.29. But 12.29 isn't really reflective or representative of the stats here, right? Because really, 12.29 is actually higher than all of these values except for one. We can see how this one extreme value, this outlier, is going to affect our data. It distorts our mean. So we have to be careful. And this is what I was mentioning, why you might want to be looking out for this stuff whenever you encounter stats in your everyday life. Make a note of median and mean. If somebody reports the mean, think about it. Is that the right stat to use? If they report the median, think about it. Is that the right stat to use? You always got to make sure, question what you see. And this is one of the ways that people try to kind of be a little bit deceitful. So it is not influenced by extreme values, as we can see here. When I had this 53, the 5 here is the middlest value. It's not affected by if this is 53 or 500. It would not matter. It would absolutely matter if it were the mean, however. Here's another example. So when I was talking about IQ earlier, the median is also the 100 in the United States as well, and that's just one of the things that the IQ test is kind of devised to do, so that it's a perfectly symmetrical distribution. So you have the mean and the median as the same value. All right. So wait a second here. let's say that the mean, and I found, this data is always changing, but the mean income is 97.962. The median income is 69,717. So that is quite a difference, right? That is a huge difference. That's a $28,000 difference, which is enormous. So if you were to go right now into Google, what is the average, individual's income in the United States? They'll probably try to just give you the median, because that's probably the best way to show it. Why? Because there are a few people in the U.S. that have an exorbitant amount of money that moves that skew. And you can kind of see that influence even here, where we have people like Jeff Bezos or Elon Musk, for example, that are really jacking up the mean value, whenever for everyone else, for 99% of the rest of everybody, their income is much closer to Earth. So the median income is about $70,000, but it's I wish that it was 97. That's more than I make. So that's why we have to pay attention to see whether or not someone's reporting the mean or the median. For example, if somebody wants to say, like, look, American households are doing great right now, the mean income is, they may want to report this, right? If that's on their agenda, they want to make things look good. If they are trying to say that things are worse, they might try to use the median because they know it's going to be a lower value than the mean. All right, so here is an example. If we're looking at like a neighborhood, for example. This is just kind of showing this using visuals. That here we're looking at this mean for this neighborhood might be close to 70,000, but that's because we have these two folks over here that are really on the far end that are kind of moving that mean further down the line. If we look at, if this is the entire neighborhood, most folks are actually over here, right? Most folks are in this part between 20,000 and 35,000. So that's so different than 70,000, right? And that's one of the reasons why we have to, again, be careful. That now we have to ask ourselves, what is the most meaningful way to illustrate this difference? Maybe use the median, maybe use the mode. Let's talk about what those are. The mode is the most common value in your data set. It's the most frequent score. So it's which value occurs the most. So in this data set right here, 5, 2, 6, 2, 4, 100, 64, 3, 2, 4, the one that occurs the most is going to be 2, and so we report that. If you have more than one mode, like let's say if we had like 3 5s in here, then we say the mode is 2 and 5. I always remembered this because it's called the mode because in French the word mode means fashion. I'm sure it's not how it's actually pronounced in French, but it means fashion or of the style. And so I always thought of like the most fashionable number is going to be the one that occurs the most. And so it, like the median, is also not influenced by extreme values, but oftentimes is actually a little bit harder to kind of interpret. For example, the mode income in the U.S. is 12,500. I don't even think that that's actually accurate anymore. Just from when I Googled it, that's what it said. But that reflects a certain unemployment, program gives 12,500 a year, and that because it's that specific number, and there are so many people making it, that is the most common number, right? That, So is that the most descriptive representative number to use to talk about household income? Probably not, right? It's probably the median. Would probably be the best for us. The mode is the least commonly used of all of these central tendency values. Now, if we're talking about dispersion or variation, there's a couple of other numbers that we can use to talk about how different our data are. And so one of those is the range, where we're talking about the highest and the lowest data values. And you've probably calculated this before in your other math classes, where you're looking at what the difference is between the highest and lowest values. So in this data set, the range will be 51 because I'm subtracting 53 by 2, and that gives me 51. All right, so that's the range. The example that I gave here, again, thinking about income, is looking at the largest, which again is always changing, but at the time of this was $146 billion and 500 million whatever. It's a lot, right? 1.146.5 billion dollars. That's what I'm trying to say. And if we look at the range for the U.S., then that means that is the range, because the lowest is 0, and that is excluding negative monies. All right, so standard deviation. Standard deviation is a super common way of talking about variation, but you're not actually going to calculate it in this class. It's something that you're going to be learning in chapter 3 or 4 of stats next semester. But essentially what it is, because you're going to see standard deviation come up a lot. Now that you starting to have language for data, you're going to start seeing these words pop up all the time. Standard deviation is one of those examples where standard deviation is referring to the average distance between different values in your data set. So if your standard deviation is very small, that means that your values are very close to one another. If that value is very large, that means that there's a lot of variability in your data, that your values are quite different from one another. That is kind of like the average distance or difference between the values in your data set. The example here, the standard deviation of income in the U.S. is about 20,000, which means that if we were to take every single person in the U.S. and try to find the average difference between the scores, it would probably be about 20,000. And outliers can absolutely make this number higher than it is. So again, thinking about the U.S., right, we have a couple of outliers that really, on one end, that are really inflating the standard deviation, when in actuality it's probably much closer to 20, closer together than 20,000 might suggest. All right, and this is true not just for really large values, but also for very, very small values too. So this is what we're talking about here, that these values right here, these are referring to standard deviation. So this is saying 1 standard deviation above the mean. This is saying 1 standard deviation below the mean. This is saying 2 standard deviations below the mean, and this one's saying 2 standard deviations above the mean. So what we can conclude from this is that roughly 68% of the data is going to fall usually between the first standard deviation above and below the mean. All right, and the outliers would be further out here in either direction. Usually anything that is above 3 standard deviations away from the mean or below the mean is considered an outlier. Here is an example of dispersion in action, where here we would say that this is looking at a not very much variability, because we have a lot of these values are really close together. And here we have a lot of values are not close together. It's spread out, it's flatter. So we say that there's more dispersion in this data. The values are more different from one another than they are in here. You can even see the extremes are way out here compared to the other. Alrighty, okay. And so, yeah, and again, you can see that this standard deviation is smaller than this standard deviation. Alright, so now is a quick halftime moment. I'm gonna chug my water for a second. Grab yourself a coffee or a juice box, a Capri Sun. Alright, so I'm going to show you some bad data. I tried not to include too much because I have a lot of examples of this. Here is an example. Planned Parenthood, Federation of America, abortions up, life-saving procedures down. So it's showing plotted on this. Abortions versus cancer screening prevention services. This is really old data, by the way. But you can see here from 2006 to 2013, we can see that it looks like abortions are on the rise and cancer screenings are on the wane. But again, always pay attention to the axes, right? Because here we have this over here is 2 million, and this is 900,000. And here we have 289, and this is 327,000. So obviously whoever made this graph is trying to deceive you, right? Because this value right here should be far beneath this one, because this number is literally 3 times larger than this number is. So that's an example of how people might try to visualize data like this to try to deceive you or try to confuse you. They're not necessarily wrong about the trends here, about the direction of the data, but it is dishonest to plot them like this. All right, so here is an example, a more lighthearted example. I didn't want to just go to political examples, but like I said, you're going to see this used a lot in the news and politics where people are trying to deceive you with this stuff. So here we have KFC is advertising their new crispy chicken twister is 650 calories. So let's plot that where we got we got KFC's right here. So it's about in the middle, right? So it looks like maybe it's not as unhealthy as you thought it was going to be, right? It's so much better for you than Taco Bell, Burger King, or Wendy's, right? But what this suggests is that pizza is good for you, but that also McDonald's is good for you, which we know is not true, right? And so again, yeah, you look over here at the axis, it's 590, right? That's certainly not 0. And so the actual truth is that there's not a ton of difference here. If we're looking at, roughly 600 to 720, those are the extremes. Come on. Do better, KFC. Come on, Colonel, do better. Here is another one. What is the European Union demanding its members pay? The current contribution of its GDP is 1%. The future contribution is 1.08%, where this almost looks like they're saying that they want it to be almost twice as much, but in fact it's actually not even 1%, not even 0.5%, not even 0.1%, 0.08%. So these two graphs are very misleading. Here, I don't even know what this is supposed to be. Somebody, if you know what this is supposed to be, let me know. I don't know what it is. I've looked at it for a long time now. When I close my eyes, I see this data. Here is another example looking at average female height per country. And so it cracks me up because here for Latvia, women, the mean height is 5'5", and then in India it is a little over 5'0". And so the reason why this is funny is because it makes it appear that Indian women stand up to Latvian women's knees, right? Like that's how tall they are. They didn't even come up to Latvian women's waists. Like it's very stupid. Here is another one looking at percentage of Americans that identify as Christians. So here you can see that the bullet point here, we used to enthusiastically be a Christian nation, and we're moving from 2009 to 2019. We're moving from 77% to 65%, but you can see that this looks like maybe not even half of the United States considers themselves Christians anymore, whenever we see that's not exactly what, if we look at the axis here, that 50% is like way down here, right? Suggesting that while, again, there may be a trend, that it is not as drastic as this data suggests. Here is an example this is a bad example of data. This is somebody trying to use a pie chart to look at nominal data. And I was telling you about how nominal data, you got to be careful, because if you use a pie chart in the wrong circumstance, you can have something like this, where we're looking at how many stocks were accounted for or whatever. And we got a lot in Apple, a lot in Microsoft, a lot in Amazon, Facebook, Salesforce, and then all of these, even the tiniest ones no one's ever heard of, they have their own slice of the pie and it just looks like nothing. Here is one of my favorite examples, and this is the final example, or one of the final examples I'm going to give you, just because I thought it was funny. Each dot represents 5,000 hogs. So this textbook is trying to show the distribution of hogs in the United States, and you can kind of see here all these dots are hogs, and so I said it was a textbook. It is a textbook from the late 80s, and I'll just let you read these comments. Each dot represents 5,000 hogs. Untapped infinite hog supply in the ocean. As you can see, all these dots out here. Each state is lined with an impenetrable wall of swine. We are trapped. That's absolutely true. And we've lost Canada and Mexico to hogs already. As you can see, they're not even on the map. It's just nothing but hogs. You look up, you look down, it's nothing but hogs. All right, so here is another thing, and this is another one that kind of gets on my nerves, where people will try to talk about how successful something is, and they'll talk about it in cumulative terms. Cumulative means that it continually adds, that we're looking at the total number. And so if you're looking at this graph right here, it seems to suggest that sales are getting better, right? But what this means is that this is how many they have sold total up here. So this graph can never go down, right? Like you'll never have from 2012 to 2013 that it went down, because it's just looking at the total number sold. Not sold per year, but sold overall. That's what makes it cumulative. And so this is an example of if you're trying to show strong sales, you might show this cumulative whenever what you should be looking at as the mean, right, to look for actual trends. Here is another example looking at the average annual global temperature in Fahrenheit. So you can see that it doesn't look like the average temperature has changed very much from 1880 to 2010. You can see that basically it's the same, right? But if you were to zoom in, if you were to look in over here to blow that up, you can see that actually it does look like it has changed quite a bit in that same amount of time, moving from 1880 over here to the early 2010s over here, that it has gone up about a degree and degree and a half, degree and a third, or something like that. So zooming in does show you some of the trends, but like I said, you got to be careful, because whether or not you find that to be somebody who, for example, denies climate change may look at this and say, yeah, that's because you zoomed in on the axis, and didn't you just say that you're not supposed to do that? So this is the importance of kind of thinking about data critically and discussing these kinds of problems, is that you have to know when you should or shouldn't touch with the axes, and when doing so is deceitful, and when doing so is just trying to help show a point here. All right. So here, I'm not going to go through these other examples because they're all just other examples of the same, of how people kind of try to manipulate impressions of data by messing around with the x-axis and the y-axis. So I'm just going to skip through these. If you want to check them out, you can. But we're on a budget here. I got to get you out of here in like 20 more minutes. So let's talk about inferential stats. So inferential stats, again, is going to be something that you're going to be talking a lot about in stats when you take it as a class. It's not something that you will have to calculate in our class, but if we are trying to determine whether or not two samples are similar or whether or not they are different, which you're going to see all the time as a psychologist, where you might say, like, which therapy is more effective, therapy A or therapy B? The way that you're going to be able to determine whether or not they are sufficiently different is by using inferential stats. That's how we are going to test these hypotheses. And this is not just true in psychology, this is true in biology, it's true in chemistry, it's true in physics, it's true in every single science. So get that straight, because I feel like whenever I took stats, I took it in both the stats department, the math department, and in the psych department. And I didn't realize that, oh yeah, every science uses stats too. So we talked about hypotheses, right? So hypothesis is going to be like an if-then statement. So if something occurs, then something else occurs. What we're going to use stats to do is to test these kinds of questions and determine whether or not they are accurate. We went over this at the very, very beginning of the semester, and because we're short on time, I don't want to talk about it too much. But this is just to remind ourselves that it's really, really hard to prove that something is true. It's much easier to prove that something is false. And so usually when we talk about hypotheses, we're talking about whether or not we can rule out a hypothesis. It's very rare for us to say that we proved that a hypothesis is true. Instead, we would say that we proved that it was false. That's more likely to. So it's more acceptable to say that you showed that something was false or was incorrect than to say that something was true, because you never know if there are certain exceptions. All right. So, for example, if a person is drinking alcohol and the person is 21 or over, which of these cards would I turn over to prove whether or not this was in fact correct? I would want to turn this one over, because if it says 17 years old and I turn it over and that person is drinking alcohol, then I know that this does not seem to be true. And this is as well drinking a glass of wine. If I turn this over and that value is less than 21, then I know that this is not true either, that is being violated. But if I look at these other ones, if it's 23 years old and I turn this over and that person is drinking alcohol, then what does that mean? Right? It doesn't necessarily mean anything. If it says that person's drinking Coke, it doesn't mean anything for this, because what we're saying is that if someone is drinking alcohol, then this has to be the case. All right, so let's talk about inferential stats. you're going to see this phrase used a lot, significance. Because ultimately what we're going to do is we're going to say whether or not the differences that we have in our samples are significant differences or not significant differences. For example, if I said my family is taller than your family because my family's average height is 5'5" and your family's average height is 5'4.5" is that a significant effect? Or is that just random variation, right? Or is it just random by chance, right? So inferential stats is going to help us answer that. How significant is that difference here? So inferential stats are going to help us extrapolate. In other words, they're going to help us take these findings and generalize them to other arenas. So by doing so, we're going to try to reduce the possibility that we've screwed up somewhere in our measurement. And it's also going to tell us about whether or not what we found is likely or unlikely. So whether or not it is likely because it just came about through chance variation, or whether or not there's something else going on here. So for example, if your family's average height was 6'6" and mine was 5'6" or whatever, there's probably a good chance that that's meaningful, right? That yes, in fact, your family is quite taller than my family, right? That is a significant thing. It's not just through random variation that happens. It might be because you have some that your family was I don't know. Represented like a bunch of NBA players or something. I don't know. All right, so things get a little bit confusing when you try to write this stuff out because people talk about the null hypothesis and the alternative hypothesis. So the null hypothesis is going to be the hypothesis that you're going to use, and I'm just looking at the time now. We're going to be a little bit longer than an hour. I'm so sorry. The null hypothesis is going to be the assumption that there is nothing different among your groups or your conditions. So I'm going to walk you through an example that's kind of this hot button issue right now, which is about giving hallucinogens and ecstasy and things like that to people that have PTSD as a potential viable treatment outcome. You've probably seen something about this in the news or read about it before, so we're going to use that. So here is a hypothesis. We're going to start with the null hypothesis. The null hypothesis, and every study has two hypotheses. The null hypothesis is going to be, this is what would happen if it doesn't actually work. So the null hypothesis would be, if we give ecstasy or Molly or whatever to a soldier, that it will not, then it's not going to alleviate their symptoms because it doesn't work. That's the null hypothesis. The alternative hypothesis, which is sometimes called the experimental hypothesis or the treatment hypothesis, is going to have some kind of prediction attached to it. So it could be that if MDMA is given to soldiers with PTSD, it will alleviate their symptoms or it will heighten their symptoms. Or you could even say it will change their symptoms. In any of the three circumstances, you're making a prediction that you're saying, okay, their symptoms are going to get worse, are going to get less, their symptoms are going to get more, or we don't know. Their symptoms are going to be different, but we don't know what direction yet. All right, so let's go through this example together. So let's say that for this study, we have a bunch of soldiers that have PTSD from combat experience. They're coming in for an experimental treatment therapy session. We're going to give half of them regular kind of counseling, but we're going to supplement that with a placebo, and then the other half we're going to give a psychotherapy, talk therapy, but we're going to, as a supplement, give them ecstasy to do that. And then after a few months, we're going to check in on their PTSD symptoms. We're going to test that with the CAPS, which is the Clinician-Administered PTSD Scale. It's kind of like the gold standard of PTSD diagnosis in the United States. Here we have some data. This is not real data. I made this data up. So we have a placebo and we have ecstasy. So here we have percentage with a diagnosis. So the higher means the more people have a diagnosis, the lower means less. So when people take placebo, afterwards, more of those people still have the PTSD diagnosis, fewer people have it whenever they have the MDMA. So does that make a significant difference? Is there a significant difference between 3 and 82, right? That's kind of the question here. That's what inferential stats wants to know. Here we have, and to me, I think that is an interesting, significant difference, right? 3%. That's That's a small effect, but it is. I mean, it is an effect though. So it does seem like maybe it does have some impact. Here, same question. Whenever I zoom out now, you can see, oh yeah, that's actually kind of a small difference now that we look at it, right? It's not as big as what that data showed earlier. So in this case, is that a meaningful difference? If we were to then bring this to the population and say, look, if you have PTSD, if you take this pill, it's going to relieve your symptoms. But if that only works for about 3% of the population, that actually might not be the successful treatment that we were hoping for, right? If 3 out of 100 seem to get better because of that, that doesn't really seem super helpful. Is meaningful, maybe, but let's check this out. So which hypothesis seems to be true then? If we're looking at these, if MDMA is given to a soldier with PTSD, it will not alleviate their symptoms, or do you think it's going to be one of these others? That it will, or that it will make it lower or make it higher? If I'm looking back at this, I actually don't think it makes that much of a difference. What that means is that if I give somebody MDMA, then I don't think that they're going to be likely, by chance, to say that their PTSD is better, because whenever we compared that with the control group, with the placebo group, basically there's only a 3% difference, which is not very much, right? So I would probably, if I were looking at this, I would run some stats on it and probably conclude, oh, I can't reject the null hypothesis. So it seems like the stuff works, but I can't say that if I give this ecstasy to a soldier, it will alleviate their symptoms. I can't say that. So I have to go with this one. I have to go with the null hypothesis, which is the boring hypothesis, which is one that's way less exciting, right? Here, now let's look at a slightly different kind of approach, where now the numbers are different because, again, I made them up. But we have the same amount for placebo, about 85%, but now we have over here about 53, 52%, right? That seems to be a bigger difference. Is it a meaningful difference, though? I would run my stats on that, and out of those, I'd probably go with the alternative hypothesis. I would probably go with it does alleviate their symptoms, because what I'm saying here is that when people take a placebo, 15 out of 100 get better, but whenever I give ecstasy, 47% get better. And that's quite a bit more than 15%. If I'm going back to this, is that additional 3% worth it? Our stats would probably say no. Here, it would probably say yes. And it depends on what kind of tests you run and, more about, your sample size and stuff like that. We'll learn more about that next semester. But basically, looking at graphs is not the way that scientists analyze data. It might be the way that most people consume their news or whatever, but it's not the way that scientists do it. Usually scientists will say, well, I want to see the data. I don't want to just look at a figure. I don't want to take your word for it. I want to look at the data. And that's because using statistical testing, you might be able to find interesting trends and patterns in this. These kinds of tests are going to let you know whether or not the data that you find are meaningful or whether or not they occur to us through random chance. And that probability is called the p-value. The likelihood that your effect is because of random chance is the p-value. The smaller that is, the more likely it is that your treatment or your drug or whatever, your group, is effective and working. In the last example, we were talking about the null hypothesis. The null hypothesis is just a way of saying that you do not think that the sample is going to be different from the population. In other words, that you don't think that there's a meaningful difference between the sample and the population, therefore it's not a significant difference. And so the p-value is going to tell you whether or not it's a significant difference, because it tells you the likelihood that that data comes to us from random variation and random variability. The standard that's used in science is 0.05. If your p-value is less than 0.05, people will say, yes, that is a statistically significant effect. That number is honestly, though, just kind of agreed upon by scientists. It is a little bit arbitrary, right? That's just the line in the sand that some scientists use, and they say, if it's less likely than this, then we're going to say that it's a meaningful trend. If it's not as likely as, if it's above 5% likely to come from random variation, that's not uncommon enough. That's not rare enough. Scientists will turn their nose up and say, yeah, I can't be sure that that's not just random variability or random dispersion in your sample. I'm sorry, bro. All right. So let's talk about statistical non-significance. What happens if you don't reject the null hypothesis? So in the first example, we didn't reject the null hypothesis, right? We ultimately said, like, look, it doesn't seem like it makes a huge difference in the population. And so if you don't get less than 0.05 for your p-value, that basically means that you can't guarantee that your findings aren't because of random variability in your population or in your sample. What you're saying is that some of the confounds that we talked about in previous chapters, like maturation or about instrumentation or whatever, that those things might be contributing to this, but we can't be sure. All right. So you might see sometimes whenever you're looking at figures or tables where they have asterisks, almost always those asterisks are going to be referring to the significance level. If something is less than 0.05, then they're going to highlight it. So if you see a table like this, then what we're saying is, like in terms of social interactions, what makes people happy, for example. That's what we're looking at right here. And what we're saying is that being alone has a negative correlation with happiness. The more people are alone, the less happy they are, and that is a significant finding because we have found it to be less than 5% likely to be up to chance and just random variability, that this had a big sample size or whatever. If I look over at talking to other people, it looks like that is, has a correlation of 0.26, and that it is also statistically significant. So it is meaningful. That means that those things actually do seem to affect behavior. If I look at this right here, a correlation of negative 0.10 means that there's a negative correlation of 0.1 with small talk and happiness. So it looks like people are less happy when they engage in small talk. But we actually can't say that because it is not statistically significant. We don't have those little asterisks showing that these researchers ran their data through some tests to determine whether or not it was statistically significant. So we'd say that that probably doesn't matter. It doesn't matter if you engage in small talk or not, that it doesn't seem to affect happiness. It's too small an effect to be notable or significant. And I say too small, I mean it's not reliable enough for us to conclude that. When we're talking about validity, validity comes up when we talk about different kinds of errors. So p-values are oftentimes seen as the end result, that if you get less than 0.05, then you can reject the null hypothesis, and you can say that, hey, my results are interesting and they're significant, and you should pay attention to them. But we should always still be a little bit careful because there can be cases called type 1 errors or false positive errors. And this is whenever our study tells our data seem to indicate that there is an interesting trend, but in reality it's just because of random variability. It does happen sometimes that even though a p-value being equal to 0.05, what that means is that it's 5% likely to happen from chance. That's not impossible, right? And it does happen sometimes where people will collect a bunch of data. They'll say like, hey, it looks like, to give a very popular example, I'll keep it short enough though, and because I think I may have already talked with you about this example, that there was a study that showed like if you balance a pen right here, like that, with your nose like that, between your nose and your lip, that people who do that for 30 minutes seem to be in a bad mood compared to people who hold it between their teeth like that for 30 minutes. And the explanation for that was because if you're doing this, you're simulating a pout, and so the article at the time was saying that by going through and making these facial interactions, if you do them, even if you aren't happy, by smiling, you might become happy. And if you pout and you're not unhappy by pouting enough, you might become unhappy. And they found this and it was statistically significant, but when people tried to replicate it, they didn't have a whole lot of success doing that. And so it could have been that just by chance that from whatever reason, that sample, there was enough variability that it seems like it looked like it was true, but when people otherwise tried it, it seems like it wasn't true. That's an example of a type 1 error. It was a false positive. It was a false alarm. If we were wrong and we said that MDMA does have an effect, but I didn't think that it did, so like if I initially said I don't think that it matters, but then later somebody else tested it and found that it does. That's considered a type 2 error. A type 2 error is when our study says that something's not significant, when in reality it does actually affect behavior. And here this table kind of walks you through that and breaks that down. All right. We're entering into the final stretch, so hang in with me. So the effect size is something that's become much more common in the past decade, I would say. An effect size is talking about how important is this difference. So significance is usually referring to likelihood, saying that if something is a significant finding, that means that it is not by chance. Effect sizes say, okay, well, is it an important finding? Which sounds a little bit judgmental, but here's what I mean by this. Here's an example that in 2018, I don't know if y'all remember this, in 2018, the National Institute of Health published a study that showed that eating red meat was going to increase your risk of heart disease. And it was through all the news, spent 48 hours really talking about it a lot, because it was basically saying, like, oh, if you're going to eat red meat, you're going to die early and all this other stuff. And it was a significant effect, and all, the researchers did everything right. But the groups weren't actually all that different. Basically what they said is that if someone is age 60 and has a 50%, but their argument was that if somebody eats red meat regularly, that if somebody is 60 years of age, they have 50% of a chance of dying in the next 25 years, which is quite vague. But that an additional serving of red meat increases that chance from 50% to 57%. So an additional 7% of dying within 25 years. That also means that some of those people might live more than 75 years of age, and they're not counted in this data. So it's very, very kind of limited data set they're dealing with here. And essentially people were like, oh, wait a second, that's it? Like, we're really talking about like a small slice of people, that it's not like a big trend like it was suggested. That 7% is an example of an effect size. The effect size is saying, here's how important that difference is. So yes, it does seem like red meat does shorten your lifespan, which is concerning. But how much? How much? That is the effect size. How much? About 7% of people will have theirs shortened. We can't say how much is shortened, but we can say that for about the population, that you're about 7% more likely for that to happen between those ages. All right, so if we were to try to apply this to our example here, let's say that we were using, again, the ecstasy and PTSD example. Here, what we would be able to say something like, going back. I'm going way back. Sorry, y'all. I'm coming back to that slide in just a second. In this case right here, that this is a large effect size, and that this is a small effect size. The difference between those bars. All right. Okay, and that is it. That is everything you need to learn for this class, pretty much. Oh man, what an adventure! Thank you so much for being here with me on this glorious adventure. And I feel a little bit of pressure now, because usually I show you something cute at the end of these videos, but I don't have anything cute. Instead, you can end the video right now. I'm not going to cover anything that's going to be on the exam. I'm not going to talk about extra credit or anything like that. You can totally check out by now. I'm going to talk for a couple of more minutes, though, in case you want to see something cute. So I'm going to show you something cute. So let me see. I found this this video of my dog Teddy. You may remember you saw Teddy. He's the big one that I have, the big old Chow Chow mutt. He's like Chow and Pomeranian. This is him at like, I don't know, he had lived with us for maybe 2 weeks at this point. And yeah, I'll just let this play for a second. Basically, I'm trying to teach him some tricks, and you can, I don't think you can hear the audio, so I'm just talking over this, that I had taught him fetch, and that he would go get stuff like this and then come back and bring it to me. And I taught him things like stay, and I taught him shake and things like that. So I'm going to let this play while I tell you a little bit of a story for the next 2 minutes. Here's what I'm going to say. And I've told you this, when I took Research Methods 1, whenever I was in your position, I thought of it as kind of a life-changing course. I didn't think of it at the time as a life-changing course, but in retrospect it actually was. And I don't expect for this to be a life-changing course for you. But what I want to say is that actually, what do I want to? Oh, here's what I want to say. Be open to yourself in college. That if there are things that are interesting to you, follow them. If there are things that you're good at, explore them. If there are things that you're not good at, explore them. If there are things that you don't think you're good at, explore those most of all. Because, oh wow, you can see my wine collection back there. I used to drink. That was back in grad school. I used to drink a lot of wine. Can't even tell you the last time I drank some wine. Now, so the reason why I say this is because whenever I was a sophomore and I took this class, I did not think that I wanted to be a professor. I did not think that I wanted to be a researcher at all. And I had heard that this class was quite boring. We got a little bit more Teddy to go here. But I ended up really liking it and really thinking it was interesting. And so I decided to take other kinds of classes because I liked this one. And that totally put me on this trajectory where I am now, where I got involved in research on campus. I got pretty close with a psych professor, and I did research with him, and then he became a mentor for me and all this other stuff. And that was all because I decided to explore a little bit. I decided that I was going to, check out something that I didn't think that I was good at. I've never been good at math. I've always been bad at math. In research, you think you might have to be good at it, right? I didn't think I was going to be good at stats, but I turned out to really be okay at it, and now I teach it, right? The last thing that I'm going to, and again, this is not about me trying to talk about myself. What I'm trying to do is I want you to think about yourself, and I want to think about you right now at Westfield. You're at the end of research methods. You're just starting your psych major for the most part. Now's a good time to think about, what areas of psychology are interesting to you. It doesn't matter what anybody else thinks. People told me all the time that research was boring, tedious, dull. I don't think that it is. I love this stuff. And that opened up a lot of doors for me. So if you are like, I really like, I don't know, I think maybe I like counseling. And your family's like, counseling? Are you sure? Are there jobs that pay that? Maybe you should listen to your family, but it's okay to trust yourself. One of the best pieces of advice that I ever got was that it's okay to bet on yourself because nobody knows the odds like you know the odds. And I say that as somebody who neither of my parents went to college, that I was a first-generation student, and when I got to college, I did not know how to study very well, and I did really, really poorly in my first year. I had C's on my transcript or whatever. And then when I went to my advisor in sophomore year, and I told her, I think I want to maybe go to grad school, maybe get my PhD, she laughed and said, let's look at another plan here. Let's see what else we can do for you. And I remember, and I know that professor's name, I'm not going to say her name, because I like to keep these videos public, and I don't want it to get back to her because she's quite old now. And I don't want to seem too spiteful. But I remember whenever she told me that when I was sitting in with advising, I remember thinking, no, you're wrong. I know that you're wrong. Because I believe that I can do it, and that I know that I'm more than what my transcript says. That I know that I didn't do my first year here at the university because my parents didn't go to college. They didn't have the tools that they could help me with. They didn't know how to succeed in college because they hadn't done it themselves. So the odds were stacked against me. My advisor looked at that, and she didn't think that I could do it. But I knew that I was willing to work to do it, and so I knew that the odds probably were in my favor, that I could do it. So this is all just to say that if you are exploring the major, you have any questions, or if you don't know where to look next in terms of what parts of psychology interest you or that you might want to explore, maybe you want to do research, maybe you don't, maybe you are interested in doing research and don't know how to start. Maybe you want to do some research and you're shy and don't want to ask a professor hey, could I do research with you? I guarantee you 95% of people that you ask that are going to be very happy you asked that, and they're going to be very happy to work with you. That it's okay to put yourself out there. If you're a first-generation student and your parents don't know what you're doing, it's okay. My parents didn't have any idea what I was doing until I graduated, and I was able to show them, a research project that I worked on, and I said, look, this is what I did, and this is what I spend my time doing, and I love doing it, and I don't want to stop doing it. And that was when my dad realized, okay, now I know how to support my son because this is what he wants to do. So, again, if you have any questions, let me know. if you feel stuck in college, you feel discouraged, you feel demotivated, you feel like you can't do it, I know that you can. Let's talk about it. You can email me. You know what my email address is. Or you can leave a comment on this YouTube video, and I'll get back to you. But anyways, thank you so much for the semester, and yeah, see you in the discussion forum. Bye-bye, y'all.